I'm Carl Copeland. I'm the CEO of Muz Motion. So we are a motion and control company. We have a brand new magnetic platform to provide motion systems to high-performance applications such as robotics, automata, cobot. Eventually, we'll move into the aerospace and aeronautical wing, but I'm looking forward to sharing a little bit about that. But really, my talk is going to be focused on robotics in the near future of robotics because, again, I want to discuss really how it connects to the interest of this group, which is AI and IoT. So, the reason why we're here, well, oh, there we go. All right. So the reason why I'm here today is Battlestar Galactica. That was my absolute favorite show growing up. It was my inspiration, and the conversation that I had with my mother at 6 years old is the reason why I'm doing today what I'm doing. Is I was looking at the show, I'm like, listen, if they're putting all this time and effort into make-believe, why don't we just do it for real? Thoughts of a 6-year-old. And so that was really the inspiration for me. And so for decades, futurists and scientists have been promoting this idea of the age, this inspiration for the coming age of robotics. So they've expanded they've inspired us, and I don't have my script in front of me, so they've inspired our possibilities, they've expanded our horizons, and really what they did was they set expectations that were really, truly monumental. And so as I continued in my journey growing up and then in my education, I started to realize really how extreme some of these things that I took for granted as a child were with robotics. And the reality is, oh no, I'm kidding. All right, there we go. So this is really what the field of humanoid robotics has been delivering for us. Alright, so in all fairness, that video is 3 years old. That was the finals in the DARPA challenge, where they invited teams from all over the globe to compete in this automata, this humanoid competition. And so they had to walk down a certain walkway, get in an electric vehicle, drive at a certain distance, and then complete an obstacle course, kind of like a search and rescue. It was a simulated search and rescue operation. That's what the DARPA challenge was set to fund. This robot here is the Atlas. This platform was the culmination of all of DARPA's efforts. And in fact, in this competition, this robot finished second only because of this fall, and it damaged an actuator when it fell, and so it lost to South Korea by 2 seconds. But you will probably recognize that this was 3 years ago. This next video I'm going to play was just published last week, and it is the same platform, and this is the significant advancements that have happened in just the last 3 years. If this will play. Well, this video apparently didn't want to make the transition for me. What you would see, and I'm sure a lot of you have already seen this on YouTube, the Atlas robot that was supposed to be playing in this video actually leaps over a log and does parkour up several steps, completely untethered, completely autonomous. And that's just in 3 years of development. Let's see if we can get the next. Well, anyway, I was going to show you this really awesome robot dog that was dancing better than probably any of us could pull off. But what would surprise you with these robotics is that what you're seeing are robots that are completely driven hydraulically. Okay, there we go. So what would surprise most people is that all these robots are hydraulic by nature. In fact, this is the old version that you saw stumbling everywhere. This is the newest version that I wish you would have been able to see doing parkour. And they're actually emulating bone structure. They are running hydraulics through the integral into the frame and using it as both cooling as well as to power the hydraulic actuators inside the robot. This particular, the Atlas model has 28 hydraulically actuated joints, and then it has some very small other moving parts that are only the small parts are using electric motors. So,
can I ask a question?
Yeah.
Why hydraulic versus pneumatic?
That's where I'm going.
Okay.
So first of all, pneumatics doesn't have the torque.
Got it.
So the entire issue with robotics and robotic motion is the torque density of the available motion systems. And so everything that's being done, all the advancements that you saw between the stumbling robots, and which you'll see when you Google the YouTube videos I tried to play you, is in actuators and the controls. Motion systems have not really changed. There's been no new technology since the 40s, really. I mean, the only thing that's really improved are the electronic controls, the geared drive, they call them drives, it's the gearboxes, the transmissions, and manufacturing tolerances and materials. Matter of fact, the electric motor hasn't changed since Tesla designed it in the 1880s and perfected it in the 19-teens. So the transformers on the poles, the motors in your washing machine, all of those are based 100% on what Tesla did at the turn of the last century. And the only improvements are in material quality, manufacturing quality, and manufacturing tolerances. And so the issue with robotics is the torque. And so they're actually, this is a hybrid platform. So you have sometimes a gasoline engine, sometimes an electric, battery-driven electric motor that runs a hydraulic pump. And then you have a bunch of electronic actuators that open and close the valves, reversing the flow of the hydraulic fluid to emulate this motion. But as you can imagine, I mean, they're getting better at doing it, but it's really a crude system. But the real future is not really humanoids, although that's coming. The real future are what are called cobots. And for a lot of you probably know what a cobot is, but for those that don't, cobot just stands for collaborative robotics. So what is a cobot? And this is locked up on me again. So let me see if I can. Oh, there we go. Okay, so a cobot is a robot that's specifically designed for safe, collaborative operation in human-occupied environments. In other words, you can safely interact with this robot. It can operate in direct contact with humans. Okay, I'm just going to go ahead and slide it. So it also can be programmed by humans through mimicry, meaning that you can input what you want the robot to do, it records it, and it can replay that motion and that torque. It responds quickly to unexpected obstacles and obstructions. It provides adaptive control forces, meaning it can change its programming to not to do an XYZ, but to literally apply the force on an object regardless if the object is in motion or not. And then it requires no safety barriers. Now, we're all familiar with the giant automotive robotic arms that are working on cars and all that, but those things, again, are hydraulic. Really, any robot larger than 12 to 18 inches is completely hydraulic, because the electric motion systems that are out there, in order to get these kind of performances, you have to use a type of electric motor. It's a high-performance motor called a servo motor. Some of you probably know what they are, a lot of you have heard of them. But what a servo motor is it's a motor that is extremely quick and responsive. We classify it as speed, but it's not RPM like most think of. It's literally how fast it can accelerate and decelerate. It's called the time constant, the mechanical time constant. So it's really how fast can it accelerate to 2/3 of its maximum RPM, and how quick can it decelerate from that. And then the time in milliseconds determines its mechanical time constant. So the lower that period of time, the better its mechanical time constant. And those motors are required because it has to be able to instantly react. I'm hoping this video actually plays. It doesn't look like it is, because to describe what it is a lot different than to actually see what it is. And it looks like the video once again has crashed our system. So if you go on Google, you go on YouTube and Google Universal Robotics, you will see this robot arm. And it's really quite amazing what they're doing with it. Now again though, they have to use these servos in order to get these kinds of performances where if you come into contact with this robot, it will sense the unexpected torque load on the motor. The motor has a real-time feedback to the system and it will shut itself down in order to prevent any kind of injury or damage to equipment or whatever. So in order to do that, you have to have a servo, but servos are extremely weak. So I like to use the analogy for non-motor people on how these motors are classified. So you have giant workhorse motors. They're called traction motors. And believe it or not, that's what moves locomotives down the rail. So we've had hybrid vehicles since the 40s, and we perfected these hybrid vehicles in the 40s and 50s, and we call them locomotives. They're a giant diesel engine that powers an AC generator that powers traction motors. Each axle of that locomotive has an electric motor on that axle. If it were not for that system, there's no way the trains could even pull a quarter of what they pull today. See, electric motors are all torque. Especially these traction motors are designed for super high torque. Not a high RPM, high torque. And without that torque pull, they could not pull the loads. Let me tell you how efficient modern locomotives are. This is probably 10-year-old specs, but the GE locomotive power plants from 10 years ago could pull 100,000 tons of cargo 10 miles on less than a penny. So when you see these hybrid vehicles out here on the road, they're a joke. They're an intentional joke, in my opinion. Matter of fact, if they're selling you a hybrid vehicle, and I own two, if someone's selling you a hybrid vehicle and it's on a gas engine, they're yanking your chain. It's that if you really want an effective hybrid vehicle, you need to have the high torque, low RPM diesel powering the electrical system that is also high torque, low RPM. That is the system that should be implemented. But again, for political and economic reasons, they keep sticking gas engines in these things. But those big traction motors, I like to refer to them as the big bull elephant. You know, that's the tractor, that's the heavy moving equipment in India and in Central Asia, is the elephant. It's a big, huge, powerful motor. Then you have the standard industrial three-phase motors and single-phase motors that like power your washing machine or manufacturing equipment. There's obviously a scale, but think of that like the different types of workhorses that are out there. Then you have high-performance motors, which are stepper motors and servo motors. The servo motor is a hummingbird. Extremely high performance, no load capacity whatsoever. So what they wind up doing in these kind of robots is they start trading all of that speed and performance, they start trading it for torque through the gearing ratio. They call them drives. And so this cobot, for instance, it's a 6-axis cobot. So each joint has 2 motors that articulate that joint. You'll notice there's a natural scale in the size of the motors. In each one of these has a 150-to-1 to 200-to-1 gear ratio inside, as connected as part of this motor. And if it weren't for that, it couldn't even lift its own weight. And these things are really quite weak. And I'm going to see if I can advance this at all. So with these motors, again, you have the bull elephant, big traction motors. You have the really high performance hummingbirds. And so the issue is that you need the hummingbird level performance for any kind of reasonable robot. But again, you have no torque. And so that's why they're stuck with hydraulics, because they're actually doing their utmost to take this high torque system and use very sophisticated controlled electronic software, trial and error, balancing sensors. You saw that one robot in the video that did play where the robot started getting the shakes sitting on the edge of that golf cart and then it fell out. What that is that's a feedback loop error, because the motion system is trying to get the hydraulic system to simulate human motion, but the hydraulics, there's latency in the pressure differentials as it's trying to change positions, and it would get caught in a feedback loop error and just shudder until it fell over. And that's the challenges that they've been addressing with electronics and actuators and control. So all of these dog robots that, that are running around, the dancing robots, these humanoid robots that are walking around, they're all hydraulic systems. And that's where we are specifically trying to address, and my new technology will address this situation. So what we have is a brand new motion platform. I call it the field modulation motor. And it is a brand new architecture of magnetics. It's a dual stator with an ancillary rotor magnetics platform. It's actually more accurately described as a mechanical transformer. So it works like a transformer where you have two different magnetic field pairs that are opposed to each other, and the rotor is simply acted on by modulating the field of using the winding to modulate the permanent magnet field on the other side, and it changes the forces on the rotor. What that gives us is that gives me a motor. I have on my bench what I call the world's first paper motor. So I have a motor that is 85% medium density cellulose fiber, otherwise known as cabinet grade MDF. I literally pulled it out of the trash bin and made the majority of my motor out of scrap cabinet grade MDF. 15% of it is the magnetics. Now, how do we do that? Well, we optimized and we miniaturized the magnetics by fragmenting them into multiple poles. So I actually have 72 magnetic poles that are configured into 18 isolated magnetic circuits. We've spread that across 3 arrays of 12 pairs. And then each one of them is completely isolated, but because we're able to put the 6 o'clock and 12 o'clock into 180-degree phases, we are able to connect those 2 phases by reversing the wires on the opposite pair. And so we wind up with an 18-phase motor. And what we really have are 6 3-phase motors on a common shaft. Now what does that mean? All the big, huge industrial motors that you see, the high torque, that are running the manufacturing equipment and processing equipment, those are 3-phase motors, drill rigs, all that stuff. And so we have 6 of those 3-phase motors on a single common shaft. And that gives us the ability to put a tremendous amount of torque into a much smaller package. And again, even in that smaller package, we're 85% non-magnetic. Now, obviously, as we optimize it down, that ratio is going to change. We'll probably be closer to like a 50-50 or a 60-40 as we reduce the fixture material that's non-magnetic, and we optimize the motor down to its optimal size, depending on the application. But what that demonstrates is the material diversity that we're going to be able to apply in the robotics field. And we're specifically targeting humanoid or automata, however you want to say it. We're targeting that market really because it's pure R&D. I mean, there's billions in public and private funds being funneled into these groups. That DARPA competition being an example. They weren't only funded by DARPA. They had Amazon, they had Google, they had SpaceX. They had all these companies that were also investing in developing that platform.
So I assume you have patents on all this, or?
Yes, I actually have. I have over 20 patents granted, and I have probably 3 or 4 dozen more that are patent pending internationally. So, yeah, so I've spent I developed the magnetic system about 25 years ago, and I've been doing this full time for about 9 years now. I finally, pulled in my lines and put down a stake and made this my full-time development. So we actually started developing this system for power production and realized in the middle of it that we had an exceptional motor, and the motors are so much easier to sell than generators. So the market's much faster. To give you an idea, now Baldor about 4 years ago, Baldor is probably the most recognized name in the U.S. for motors. They sold to a company called ABB, but prior to that, they owned the largest market share. Matter of fact, their market share in the motor market was more than their 2 closest competitors combined, and they own 6% of the U.S. motor market. That's how diverse and fragmented the motor market is. And so, being that the market was that diverse, and being that it was very, we had a system that was going to be in high demand, especially in high performance motion, then it was a no-brainer for us to kind of shift gears and go into the high performance motion system side. And so, what our new motor delivers is it delivers a 30-to-1 advantage in mechanical time constant. So we already have servos that are high performance hummingbirds, right? Our motor can respond 30 times faster any same class, any servo in the same class, meaning the same size. But on top of that, we have 10 times the torque of any other servo. We actually have torque that rivals or matches traction motors. So what we end up with is we end up with a bull elephant with hummingbird performance. And so this is the holy grail of robotics. And so the linchpin in robotics has not been the software, has not been the hardware, has not been the electronics, it has been the motion systems. That's the limiting factor in this whole equation. I mean, we've had the hardware and the electronics that could do this for a long time. They're getting better, they're optimizing it, they're figuring out the software. But all of this is an attempt to overcome the limitations of the drive systems. And so with this new motion system that we're hoping to, we're looking to engage the automata. I'm in the final stages of getting a production set of controls completed. We're expecting by Q1 next year to have that done. We'll start engaging these automata people who have they prefer in-development technology. So we don't have to go through and have production lines or anything. They're wanting to dictate how the controls are designed for their purposes. So we're going to be engaging them in Q1. And by Q3, we'll be into the Cobot space, which is a little bit more of an OEM product line that we'll have developed through our automata partnerships. And so this new motion system is going to completely change the face of robotics. What that really means for us is like how will that directly impact? There's a lot of fear mongering out there. There's a lot of misconceptions out there about what robotics are going to do, how are they going to affect the job market, how are they going to affect manufacturing. But the thing is that we as human beings, we are not ideally suited for repetitive rote operations. We're masterful at what we do. What we're uniquely engineered for is dynamic thinking and creative problem solving. That's how the human is wired. The robots, on the other hand, they're not creative thinkers. They're not problem solvers. It's data in, data out. There's a lot of hype going on about AI. The Hollywood media narrative on AI, and this is my opinion, and I know there's some other people in here who may know more about AI than I do, but in my experience and research, it's all hyperbole. It's all gross exaggeration and Hollywood perspective. There's not a computer on the planet that doesn't output what a human input into it. Now, don't get me wrong, AI is real, but what it is it's a sophisticated and elegant way of processing data and delivering results. And as we humans get better at defining our problems, we get better at putting that into an algorithm formula that then the system can take the cognitive load off of us and do it quicker without the human frailties.
Good. Do you have any questions? Because he's covered a lot of ground here. So
I'm going to do it. I'm almost done.
Yeah. Okay. Good. Because your information is awesome, but some of it is so condensed.
Right.
So and not having the slides, is a challenge. And we do have the video if you want to do that.
Okay. Very good. And so what AI is genius at is, again, replicating what we've already been able to design, and it's really great at absorbing data, analyzing data, and giving results so that the critical thinking humans can then make decisions on how to best address that problem on the next round. So where AI and robots really are is in augmenting the human condition where we are not ideal at constant repetitive tasks. And that's where the robots are really going to shine. That's why these cobots, these manufacturing robotics, that's the future of robotics. The automata stuff is cool, it's sexy. Yes, we'll have in-home servants, and we'll have, but it's not going to be sentient. It's not going to reach singularity. It is simply going to be an expression of ourselves. And I like to say that all the fear mongering over our robot overlords is really our anthropomorphic loathing of ourselves, our baser nature. So the robots have no desire or need to do any of those things. That's all us and our own mental state. So what AI is really great at is taking what we come up with and replicating it perfectly over and over again. Universal Robotics has a video that I encourage you all to go and look at, and it shows a lady in a cabinet, speaker cabinet shop in Canada. and they do a 36-layer French polish on every single one of their speaker cabinets. And they had one lady who was a Guatemalan immigrant, barely spoke English. She came, migrated through the U.S. into Canada, and she was their #1 expert. They're a master craftsman on these things. They couldn't even get her to train other employees to do what she did. She was their single most valuable asset. And so what they did was they invested in these universal robots. And they hooked her tools to the robot, and they had her do her job while the cobot recorded all of her motions and forces and activities. And now this lady goes from $15, $20 an hour job to a $50 an hour cobot supervisor, cobot engineer, manager, where she has 4 to 6 cobots replicating her master skill while she does what she is ideally suited for, which is creative problem solving, dynamic thinking, constantly coming up with new and better, more efficient ways. She then teaches the cobot to do it. Now their entire product line has 6 of her instantly replicated. That's what we are ideal at. That is what we should be applying most of our skill. Now don't get me wrong, a master craftsman doing his craft with his own bare hands, that's never going to go away. That's a beautiful work. But the majority of our manufacturing and our processing should be done with these autonomous computers and autonomous robots, so that we don't get the repetitive injuries, we don't put ourselves in hazardous conditions. You know, they should be doing the mining and the manufacturing and the construction. Those are the things that the cobots will be doing for us. Now, one of the things about our motion system is, for a servo, about 4 inches is the end of the world. We call it size 42, which means 4.2 inches. That's about the end of the world, practically, for a servo. Now, they do have 6 and 8. I've even seen a 12-inch servo, but you wouldn't want to buy it. I mean, the performance is because of a factor in the motor is called inductance, which is a buildup of magnetic field in the iron. So as it gets bigger, there's more iron, it builds up more inductance. So it really reaches its most practical and optimal size at about 4 inches. And that's the limit of a servo. With ours, because we have fragmented and fractured the magnetics, and we're able to control the iron and minimize it, again, we're 15% of what a normal motor would be. Because of that, we can completely control the induction, and we can scale our motor to greater than 50 inches. What does that mean? That means we're talking about 40-foot Pacific Rim level robots building buildings, building bridges, I mean, doing industrial tasks. Now, they're not going to look like the Hollywood versions, but now you're talking about robotic cranes. Imagine a cobot the size of a crane building skyscrapers. So you've got humans again, experts in concrete, experts in engineering and structure, experts in foundational work. Let them handle the intelligence side, the problem-solving side, and let the robots do the difficult, hazardous work. And that's the future of robotics. And again, what's the IoT connection to all of this? Well, what you have when you have one of these robots is you have a massive walking sensor array. So there's dozens of sensors per motion system in these things, not to mention all of the other environmental sensors in order to find its position and maintain balance and maintain location. So what do you get from that? Well, you get massive, copious amounts of data. Again, this is where AI shines. Is we as humans, we can't process that. But we dump that into an IoT system, and we allow the AI in that IoT system to analyze the data. And what do we get? We get real-time torque, real-time performance, real-time maintenance monitoring. We can do preventative maintenance based on resonant feedback through the components. Our motor, for instance, has 36 windings, as I mentioned. Well, what we can do with that is the off windings can be used as integrated sensors, where we can actually, without the expense of Hall effect sensors and optical sensors and encoders, we can actually read the real-time torque on the shaft in the motor, tell so when you're running a motor, there's actually a torque difference between one end of the shaft and the other. You can read, I'm trying to think of the word, but you can read the torsion differential between the 2 ends of the motor and get a real-time torque reading, meaning you can push a motor to its optimum operating performance.
You mentioned all the sensors. How are all the sensor signals getting back to the? Is there one brain? Are there multiple brains?
No, that's a good question.
Is there a good diagram for how those are wired up?
There is. That's now sequestered onto this thumb drive. So I talk about motion systems. So a motion system is a holistic package. So each articulated joint has its own motion system. And what you have is you have what's called a motion controller, which is an electronic brain. It's the software with all the logic. Then you have what are called power controls. It's the power electronics that basically turns the voltage and current on and off for the motor, handles the heavy load. And then you have the sensing in the coils, but that package is all, and then usually, sometimes depending on how small you want the motor, you have a geared drive for that motor. So all of that makes up a motion system. And so that system is getting commands from the overarching control system for the robot. The robot says, I want to do this, and then the motion controls decipher what the motor needs to do to make that happen. And so there's every single motion system has its own bank of controls that are feeding intelligence back to the central management system of the robot. So yeah, each single motion unit, so all 28 of those things have probably 8 or 10 different data inputs coming off that motion system that then feed back to a central system.
There was something different about the armature as well, right? Where you could actually use aluminum.
Oh, yes, yeah. So one of the key factors of this new motion system of ours is the material diversity. So first of all, there's the ability to make 80% of it out of non-magnetic material. But we also, what we did is that motor is over 50% hollow, depending of course on the scale. So there's nothing inside. All of the magnetics are on the outer extremity, and the windings are on the most outer radial extremity. What that means is we have the ability to easily cool those windings. So whether we air cool them, liquid cool them, or however we decide to do it, because in the normal motor, all of the magnetics are on the inside of the motor, and so you have this giant chunk of iron that's got heat sink that's just holding heat. And the heat failure is what really causes a motor to fail. You burn up the windings. You're either going to lose a bearing or lose a winding. That's all that can go wrong with these things. Well, with ours, we can completely control the heat because it's on the outside extremity of the motor and it's broken up into smaller windings that are easier to dissipate heat with. As a result, instead of using copper, we can now use aluminum windings. Now, why don't we use them now? Well, because aluminum has a natural oxide coating that forms the second it comes in contact with air. That is one half of the component of a compound we call thermite. Thermite is the hottest burning compound that we have. And so, if you remember, like all these houses that were built in the 70s, aluminum wiring were burning down, so now they banned aluminum wiring. That's because the heat in the wire, if you had a short that raised the current, raised the voltage, it would heat the wire up enough to ignite that oxide layer, thus burning the whole place down with the thermite level reaction. With our ability to cool the heat, we are no longer worried about building up heat in the motor to the point where the windings ignite. It takes much higher temperature for copper to ignite than aluminum.
Yes, sir. Could you talk us a little bit about your rapid prototyping and manufacturing process?
Yeah, I'll get there. Yes, sir. And so on the aluminum winding, what we can do is we can control the heat so that we don't have that spontaneous combustion issue, meaning now we can use aluminum. Now, what does that mean? Well, copper is about $10 a pound. Aluminum is about 40 cents a pound. So that gives you an idea of the scale of economics. Plus, now that 80% of the motor is non-magnetic, it's not metal, it's not a rare earth mineral magnet, it's not copper. We can injection mold it, we can make it out of, again, now the paper motor is not a practical usable motor. I mean, it died in about 6 months just from humidity alone. So I broke that thing a while back. But we're doing plastic, I'm doing one right now, it's called phenolic, which is 80% recycled paper and 20% thermosetting resins, Bakelite, like the old phones, but it's been structurally reinforced with natural fibers. And so we can CNC machine that, or eventually we'll be injection molding the majority of our motors, and they'll actually be integral, just like that hydraulic one I showed you before. The motors will be integral into the robot's frame and joints. And so as you imagine, the economy of scale when you're injection molding with aerospace and automotive grade plastics, it really will enable us to produce massive quantities of motors very rapidly. It also will really drive down eventually. At first we're going to be high margin motor because it's all one-off, all custom, but as we begin to grow in our scale, the price of our motors will significantly drop just because of the commodities alone. And so Todd mentioned the rapid prototyping. Again, because of the unconventional materials, this means that we can do additive manufacturing, CNC milling, injection molding. And so another one of our kind of disruptive technologies in this is right now, if you want a custom motor, first of all, you're not going to get a custom motor unless you start your own motor company. One of the gentlemen on my advisory board, his name is Dan Jones, and he is a legend in the motor field. He's the keynote speaker at pretty much every motor drive conference in the Western world. He designed and built by hand all of the motors on the Moon buggy, as well as on the Viking Mars, the very first Mars rover, the Viking program. So, old salt, cadriel dude, brilliant. He's forgotten more than I'll ever know. And he says this about motor companies: they are dinosaurs, thoroughly set in concrete. Like, they will not change, don't want to change, and because of China, there's penny margins on most of the motors you see on the shelf. I mean, there's extremely thin margins, so they're not going to retool for anything. So a custom motor is really an off-the-shelf motor with a custom drive and custom software controls. That's all a custom motor is, and it takes you 6 weeks to 6 months, depending on the level of customization, to get those motion systems. Siemens is bragging that they're working on, again, off-the-shelf motors, customizing driving controls. They're working on turning that around in 3 weeks. So as long as it's a simple standard operation, they'll give you a custom motion system in 3 weeks. What we're going to be able to do, because we can do additive manufacturing, CNC milling, is we're going to be able to turn that into 5 business days. So we'll be able to take, once they approve the application requirements, we'll be able to produce 40 demo units and deliver them and have them on their desk in 5 business days. So, you know, most people think that the big eat the small in business. Actually, it's the fast eat the slow. Just looking at you today. You know, as long as you're quicker than your competition. And I'll tell you, a prime example of that is Nucor Steel. I don't know if any of you are familiar with the story of Nucor Steel, but there's this little small family that decided they wanted to go into they were doing recycling. They decided they wanted to go into use the recycling business, start steel manufacturing, and they started where no one wanted them. They started in T-posts, and so that was not a market that anyone cared about. Now they're the largest steel producer in the U.S. because they were quicker and faster, more versatile, and they stayed under the radar of all the big steel companies. And now they are the dominant company. And that's a little bit of our model, which is we have a new platform that's really going to be unrivaled in the high-performance motion system, and then we want to also be quick so that they can't catch up with us. So that's the rapid prototyping side.
So you're looking forward to becoming your own manufacturer instead of licensing the technology?
Yeah, so I went the licensing route. I had several conversations with several different motor companies, and what they were interested in was destroying me. So they don't want to retool. They don't want to change their product lines. They don't want innovations. And plus, you have to understand that in motor engineering, it's pretty much been accepted that we hit the physical limits of motors in the 40s. Like, everyone's just kind of accepted that. And so what we're doing is very different, and they just don't want their market disrupted. And so I tried the licensing, and I realized that's not going to happen. As a matter of fact, Dan Jones was one of the gentlemen who was going to help me, and he came back to me and said, in my entire 60-year career, he'd only seen one time where a motor company licensed anything, and it was from a relative. So they're not going to do that. So I'm to the point now where we're having to become a full motor manufacturer rather than just licensing that. And that's why I stood up Muz Motion. As my R&D lab is called Floor 36, and that's where I've been developing the technology for the last 9 years. And when we realized that we weren't going to be able to do entry to market through licensing, we stood up Muz Motion to design and produce these high-performance motion systems. And so, that's kind of the rapid data dump. And so I'm ready. I'd like to take any questions you guys have.
In terms of who your earliest customers would it be like DARPA stuff like this, or kind of what's kind of the initial you make stuff, and then who's the initial?
It's a great question. So really, some of the most optimal applications for our system I see is aerospace. So keep in mind now, there's some metrics I left out because I didn't have my prompts there. So our motion system is not only 30 times faster with 10 times the torque, but because we have that level of torque, that means we can make the motor 1/10 the size for whatever of a conventional motor for that application. Plus, because we're non-conventional material, like my paper motor weighs 5%. Now you measure a motor with what's called torque density. So you say how much torque, or how many newton meters of torque per kilograms of weight. Our torque density is 5% of the torque density of a normal servo motor. So when you think of the motors that are on an aircraft or aerospace vehicle, it's $10,000 a pound to put something in orbit. So if we take a 5-pound motor and make it half a pound, how much money is the aerospace program saving in that? And so that you would think that would be our ideal market. However, the regulatory hurdles to get something through testing and development and all that are outrageous. And so what we're doing is we are targeting automata and cobots. Why? Well, cobots wasn't even a market until 2015. That's when the advancements from the automata industry were trickling into consumer or industrial level applications that are now called cobots. And so we're in a fledgling market on that side, and then the automata people, they're all R&D. All they care about is getting published ahead of their peers, being the guy who has the best robot on the block. And they put billions of dollars into each one of those. Or that Atlas robot, that was a $50 million program. That one robot took $50 million to get there. The one that was falling over, by the way. I have no idea how much they put into it to get it doing parkour. So, matter of fact, if you could pull up the video on the parkour, that would be tremendous. Like do the Boston Dynamics Atlas parkour. So that's why we're targeting. First of all, they're early adopters. So the automata guys, they want it in development. They don't want a finished product. They want to be able to dictate and input. So in essence, what we get is called NRE, non-recurring engineering. And so we go to them, they tell us the application parameters, they pay us to develop it, they collaborate with their knowledge set in helping us develop it, so they pay me to help me develop my product line, and then when we're done, we turn around and take that finished product line and we go into the cobots and we become their OEM provider to their motion systems for their robots. So we're not building the robots, but we're empowering the robots. We're powering the future of robotics. And so that's why we selected automata, because we can do, they'll cover a majority of our R&D costs just in that collaborative effort. And then, this is one of the videos I wanted to play for you. This thing, that's just awesome. That's just really awesome. Yeah. This is the one doing parkour. So if you go to Boston Dynamics website, they'll have the single video feed.
You worked out pricing and margins?
Yes. Yeah. So going in, these guys are willing to give me their kidneys for these motion systems.
Margin is 8% of the kidney, 9% of the kidney?
Yeah. I mean, so we're talking about units that I can sell for 15 grand a pop that would probably cost me $500 to $600. Yeah. But we're doing a lot of customization. Yeah, and we're doing very, very short time. Maybe that Atlas, there may be 5 unique motion systems, and I may be giving them 20 of each one of those for backups and replacements and so forth.
Eventually you go to volume and then you get it out there.
Yeah, and so once we start injection molding, so when we do an OEM product line, we're either doing a full integral into the robot itself, or if we're doing plug-in modules, like once we go to injection molding, the price is going to significantly go down with that same profit margin applied to it. So that's our goal. And so we're trying to monetize this. I mean, automata and cobots are low-hanging fruit. I mean, it's no barrier to entry, no regulatory hurdles. Matter of fact, to get your UL certification or CEC certification, that's on the end product, it's not on us. So they have to send their entire unit for UL certification, so we even avoid that very costly and timely process. And so that's why we kind of selected to being the OEM motion system provider. Yes.
So basically, you have no interest in building a complete robot over yourself.
Well, that's not exactly accurate, because we want to build like some really great demonstrations of the platform, and literally our internal objective is to build the world's first life-size robotic T-Rex. Life-size T-Rex. And I'm not joking, that literally we're already designing it. but it gives us a full range of motion systems from large to tiny.
You just did a flip.
Oh yeah, see that shake? That's one of the feedback systems where there's having feedback error. And then, so I'm working directly with the team. The IHMC is actually the ones who developed all those motion systems, and they had to do 40 runs to get that one backflip sequence right. They had to do 10 to get the parkour one right. So there's a lot of smoke and mirrors with this too. Yes.
Carl, didn't you say that robot though can only pick up like 20 pounds?
So that's a good point. So I don't know how many of you are familiar with Rethink Robotics. Have any of you guys seen any of that? So there's there were two major cobot players in the U.S. One of them is Universal Robotics, which is the one I showed you, and the other one was Rethink Robotics, which was founded by the co-founder of iRobot of Roomba fame. He's also highly integrated into the MIT robotics lab. Well, I had a colleague of mine that just 2 weeks ago today went and did a tour of the Rethink facility, was looking at their latest cobot, the Baxter series. So the Baxter was the first one, Sawyer was their second edition. Sawyer was their high capacity cobot. It had a maximum load capacity of 8 pounds. 8 pounds. That's all it can do. And that was only at 1/3 of the arm's extension. It couldn't do 8 pounds all the way out. The Universal Robotics, theirs is a 10 kilogram or 22 pound load capacity. But again, at 1/3 of the arms. But that's a significant advantage. So my colleague did a tour on Friday. On that Wednesday, they shuttered Rethink Robotics because they were getting skunked by Universal.
So I'm not familiar with like the terminology, but are cobots, are they also lumped in with the exoskeletons, or is that separate?
Actually, cobots are considered a separate market. They're considered those arms for industrial use. However, I consider powered prosthetics a part of cobots because they do have to be able to safely collaborate with humans. And there's a professor at MIT, Dr. Hare, and he has some amazing, they call them biomechatronics, where they literally, he's a double amputee above the knee, but they're able to read the nervous impulses and muscle twitches in his legs, and all of his lower limbs act like real limbs. And he can actually sense when he steps on something. He can sense when something's stuck to his shoe and shake it off. It's almost, he said, it's other than no pain and no fatigue, it's like having his limbs back. His brain doesn't know the difference anymore. So I would consider powered prosthetics. Here it is. This was last Friday. This was published. Look at how it intuitively reacts, just like a human twisting his torso as it goes up. That's just amazing. To go from those falling over, clumsy, bumbling things in 3 years to that. And again, that's all in actuators and software and controls.
Just a word about the power of this particular motion system. The focus has been on robotics and replacing the hydraulic system with robotics. It's a powerful enough electric motor that it can also replace hydraulic systems in aircraft. Every single one of us in this room, when you fly, your life depends on hydraulic system, unless you're flying a Piper. And Bell Helicopter has come out and made a point to tell their engineers they no longer want to build an aviation platform that has a hydraulic system. So the aviation market, when you can, and trust me, I've got 2,700 hours flying in hydraulic systems. That is a single point of failure. When the hydraulic system craps out, you jump out of the airplane. So this is a life-saving technology.
Big question. So this new video, does this have any other technology?
No, this is still that same hydraulic. All they did was improve the controls and actuators. So this is purely hydraulic. Well, I'm working with IHMC, who were the ones who facilitated all those actuators and control systems. But I don't have my breadboard controls done yet, and so we're not integrating into any of their products. So I'm trying to complete my controls by the end of this quarter, so that I can engage them in January.
Just a quick question. How do you think you will be able to improve on this?
Okay, so these. Yeah, so these, okay, so he's asking how my motion system would improve on this robot. So what you're seeing this robot do is the maximum performance it's able to do. It's barely able to power itself. And it's got a load capacity limit of no more than 10 kilograms or 22 pounds. If it tries to pick anything else up or move anything else, it's pretty much going to fail. That's the most it can lift. What we're going to be able to do is give it human performances and reflexes. So I have a torque speed curve that was actually provided to me by HMC. And what they did was they gave me the torque speed curve for a hip knee joint. This is what the torque speed they would need for that. And our motion system would meet or exceed that requirement. Meaning the Hollywood idea of robots stronger than humans And at the performance level of the highest performing athletes, that's going to be the reality of robots with this new motion system. And we haven't even begun to optimize the platform, by the way. There's miles to go to optimize this platform, so we expect even more as we use better materials and really optimize our system and understand magnetics.
Are you already capitalized to scale this, or are you raising?
I'm currently raising capital. And to be honest, it's been a challenge. I have a very high-tech product for a very high-tech customer. And most of the people, at least I'm in the forward side of the Metroplex, and I hit what I call the revenue wall. These people, I give them the pitch, and their eyes roll in the back of their head, and they go, "Well, real estate oil is really my thing," you know. And so getting, you know, it's finding that person. Well, and no one wants to invest in anything in liquid right now. I mean, all the people I've talked to, they're just not putting anything in that's illiquid. And so I kind of run into that challenge, but I've also got some plans in the works to see about self-funding as much as I can as well. So there's the quick way to market, which is to find the capital, and then there's the painful way, which is the way I'm running right now. Are there any other, anybody have any other questions or any thoughts? Yes, sir.
Do you have any videos that do like a direct comparison of like an off-the-shelf servo with one of your style devices that would effectively either cost the same or have the same performance?
No, I don't. Again, we're trying to finalize the controls. And I have to tell you, part of the challenge I faced is that because of the way we're doing a completely divergent form of magnetics, there's no ability to simulate it or emulate it. We've had to do just down and dirty Edison level rote iterations. And we've had to iterate, we've had to do empirical testing, we put that into what I'm calling a design guide. We go and put all the hard data results, we see if we can extrapolate on scaling and sizing and optimizing. We build another one, we see where we were right, see where we were wrong. And so that's been a 2-year process. And we're just now at the point where we have the motor at that performance level where we're ready to enter the market. We actually expect with this phenolic version, the metrics I gave you, we're actually expecting to exceed all of that because we're not using paper anymore. So, no, I don't have the controls completed because we've still been trying to figure out the magnetics, and that's what I'm trying to get done by the end of this quarter. To get the controls done, and then we'll be able to do, what we'll be doing is we'll be going directly to my automata partners, and we'll be demonstrating the torque speed capabilities, and then we'll be integrating into that Atlas platform, and that'll be our kind of coming out moment.
So the control system for the motor is different than the average control system for
Our motor is completely unique and requires a completely proprietary unique set of controls. Yeah, absolutely. Because we have to control 18 phases. And one of the things about the way we've done it is not only do I have the ability to run with traction motor torque at a servo performance, but it's actually a multi-performance, it's a hybrid motor. We can do stepper mode or servo mode. We can switch modes on the fly, on demand. The controls will immediately switch to whatever that requirement needs. So we can do the holding torque of a stepper, or we can do the precision of a servo, or we can do just raw torque of a traction motor, but moreover, I can actually rewind the coils dynamically. What we do is we wind the windings with multiple strands, and then we can use the controls to take them in and out of series and parallel. And so if we need high torque, we just rewind it into parallel. And we drop the voltage, increase the current, we get high torque, and then when we need the speed, we can rewind it back into series, and then we can drive with the voltage and drive with the speed. You know, you're always trading torque with speed. We just have more torque to trade with our speed. But no, but again, that's one of the holdups of the controls. We can't do an off-the-shelf control because I have to control 6 3-phase motors completely synchronized. And it has to have error correction. Because as you can imagine, 36 windings, there's no way they're perfect. And so the system also has to be able to read any anomalies between the different windings and be able to error correct in order to get the balanced operation. But that's one of the things I left off is we're actually mechanically torque balanced as well. So normally in a permanent magnet machine you have cogging torque where the magnetics are attracting to the iron. We have ours, it actually has 36 individual positions in the motor. No one rotor position, only one is in direct phase at any one time, and as a result it negates all what's called detent torque or cogging torque. So we have that advantage. we eliminate those losses, but moreover, that also, because of the complexity of the timing of 36 individual firings, that's another reason why the controls are part of the bottleneck.
Awesome. If you would, let's thank them. Yeah.